Hello, everyone. Um, my name is Pei, and I just graduated this last year, 2021, from Brigham Young University, and I'm very happy to present my work. And I want to thank the organization committee for this wonderful workshop. So, the topic of my presentation is semantic network interpretation, and this is a joint work with my advisor, Ryan Farrell. So first, I'll give some background on network interpretation and understanding. So people usually think deep learning or deep neural networks are black boxes. When something went wrong, usually you don't know what to do, and you just stir a pile of linear algebra and try to make it work again. So sometimes deep learning is called the more modern alchemy. So how can we tackle this problem to make networks interpretable and understandable? So perhaps we can draw some inspiration from modern physics, planetary physics in specific. So Tycho Brahe, if you know about him, he is famous for his observation of planetary movements. He made very good notes of what stars, where the stars are at different times. And Johannes Kepler is one of his students. And Johannes Kepler makes use of Tycho Brahe's notes to came up with his 3 laws of planetary motion. So I think this is a good example of how we can think of network interpretation and understanding. So there are many different definitions how we can define interpretation and understanding. But in my opinion, network interpretation is to know what features a network has learned. So this can be compared to Tycho Brahe, to his astronomy observation, to observe things. And network understanding is to know why such features can be learned by certain architectures, or how we can learn good features. And this can be compared to Johannes Kepler's theoretical models, explaining the observation and make predictions about the unknown. Previous works, most of them do approach network interpretation by visualization. There are many different works how you can visualize a network. And here are some examples. For first layer filters, the simplest way is just visualize the filter itself. It only makes sense for the first layer, though. For deeper layer filters, if you realize it doesn't make sense because the deeper layer filters doesn't operate on the image itself. So basically operates on a composition function of previous layers. So how about deeper layer filters? There are different ways to visualize them also. One is to visualize the feature maps, like in this toolbox developed by Usinski. By visualizing the feature map, you can roughly see which part of the image the network, the filter is interested in, to get some idea what the filter is looking for. And you can also visualize the filter by finding the maximally activated images. Basically, you go through your data sets and you record the output of the filter for each image, and you find the images that get the highest output. Those images contain the pattern that a filter is interested in, like the examples below. And there is another way to do a filter visualization is to to get an optimal input for this image. Basically, you do gradient descent into the image itself and find an image that can, again, maximally activate a filter. Usually, this is done with regularization, because without regularization, you can easily get a random image that doesn't make sense. And you can people use this technique to generate lots of beautiful realizations, deep dreams, something like that. And if you compare datasets, examples, and optimizations, you can actually see one of the advantages of dataset examples that I quote here. So this is from a DistillPub article, that dataset examples have greater diversity, meaning in the dataset samples, there are different patterns you can find that a filter is interested in, instead of just one optimized input showing just one pattern. And we'll see later that this is actually quite common in convolutional neural networks, that a filter is interested in not only one pattern, but also several quite different patterns. So another important research direction is the so-called attribution. Basically, it tries to find which part of the image that influence the final classification decision. I saw some previous presentation today, and people use this method a lot. So there are different methods, and one of the earliest method is called CAM, class activation map, and there are many follow-ups. So what CAM does is basically it gets a weighted sum of the final layer feature map, and kind of mask it onto the original image to show the most important region for a certain class. However, there are several problems with realization-based interpretation methods. In this paper, saliency checks for sanity checks for saliency maps. If you randomize one layer inside a network, basically you set the weights to random numbers, you can get roughly the same or very similar saliency maps, and which doesn't make sense. And the author tried on different realization methods and find many of them have this kind of problem. And another problem with realization is it lacks semantic information. If we want to know why the network think this bird is a Carolina wren instead of a house wren, if you do CAM realization, you see roughly kind of the same realization. You don't know exactly what semantic feature triggers the network thinks it is class A instead of class B. So there is a previous work that kind of address this problem named network dissection. But one of their limits is they associate a filter with only one concept. Like we discussed earlier, a filter often is activated by several concepts. And so that's about the background. And next, I'll talk about our paper, semantic network interpretation. Basically, we came up with a representation that that can interpret a network using semantic information. And our interpretation comes at two levels. One is filter level, one is decision level. At filter level, we represent a filter with the so-called filter attribute distribution. So it's a probability distribution over a fixed set of visual attributes. And the probability of, and the number of each element shows the probability that certain attributes can activate this filter. So for example, here we visualize a filter in a network, and we show on the right that the filter attribute distribution of this filter. And you can interpret this as this filter is interested in long orange bill, long white neck, long neck, black crown, and it's both semantic and quantitative. We can do careful calculations and get some interesting results from this representation. And that's the filter level interpretation. For decision level interpretation, we want to know that when a network makes a decision, what attributes, what visual attributes or concepts is behind this decision. So in simple words, we basically, we do filter level interpretation for each final convolutional layer filters. And then we do kind of a weighted sum to get the class decision level interpretation. In this case, the network thinks this bird is a rose-breasted grosbeak because it thinks the image has black crown, black head, red breast, and white breast. So another way that we can derive this decision level interpretation and filter level interpretation is through a Bayesian inference framework. Basically, we'd like to know the probability of an attribute T activates a filter F, basically P of T given F. And if we know a little bit about the Bayesian equation, basically is prior times likelihood. So if you're interested, you can, I'll refer you to the paper to see some more details. But basically, you can think of it as a weighted sum of the filter level distribution in this case. So so next we'll show the application of this semantic interpretation. One is to do textual summarization. Basically, when a network makes a decision, we can generate a natural language that summarizes the reason behind this decision. Because we have decision level attribute distribution, the simplest way to do this is to just pick the top 5 attributes and kind of fill it in a template. In this example, we can see, for example, image A, the generated text is, this is an American pipit because it has short beak, yellow and white breast, brown crown, and yellow throat. So this gives you a kind of a human understandable way to know behind what makes the network think this way. And textual summarization also can help us to network debugging. Network debugging is just like when you debugging a program. When something goes wrong in a program, the interpreter or the compiler just throw out an error message. in this case, um, we generate a textual summarization for a network decision, and we can summarize the common failure patterns of a network and try to figure out which the future directions for improvement. And in this example, we see that sometimes the network is wrong because it didn't find the correct feature, or sometimes because the image is distorted and the filter for blue body is mistakenly fired to make the network think it's actually a bluebird instead of something else. So yeah. And that's about network interpretation, to observe what features the network has learned. What about network understanding? So actually, the filter attribute distribution can help us to understand a network, to know what makes a good feature and what makes a network better than the others. So in this research, we focus on two kind of metrics of a network. One is filter selectivity, one is concept sparseness. Filter selectivity refers to its ability to only fires or activates on a small number of concepts instead of a wide range of concepts. And concept sparseness refers to the fact that a concept is represented by several filters instead of one filter. We'd like to know the relationship between a network performance with its filter selectivity and how its concept is encoded in its filters. So kind of takeaway message that if we study the correlation, this is another task. If we want to study the correlation between the filter's importance and its selectivity, we can just delete this filter and see how the performance drops. And because we know its selectivity, we can kind of know that if we delete a highly selective filter, that the performance drop like more heavily than like less selective filters. Our finding is that a filter's importance is surprisingly negative related to its selectivity. Basically, if you delete a less selective filter, it has a greater impact on the network performance. So we hypothesize that the reason is because an important filter may encode some rare concepts, and a less important filter may encode concepts that are already encoded by other filters. So if you delete it, that doesn't make too much a difference. And about the concept sparseness, we find that generally better models encode more concepts, and the concepts becomes increasingly distributed in the filter during training. So yeah, that's it about my presentation. And if you have any questions, feel free to ask. Thank you.